Our first speaker today will be Damanvir, who will be talking about proofs of Berkovich and Uncu's conjectures on integers partition using Frobenius numbers. Please stay muted throughout the entire 15 minutes and maybe wait until the last 5 minutes for questions so that we don't have to interrupt Damanvir. Thank you.
So, thanks a lot for this opportunity. I hope you can see my screen. I will share again. So, hello everyone, I am Damanvir. Today I will speak about our proofs of Berkovich and Uncu's conjectures using Frobenius numbers. So we proved 4 of conjectures of Berkovich and Uncu regarding some partition inequalities. For the first conjecture, they defined 2 sets, CLS1 and CLS2, where CLS1 denotes the set of partitions with smallest part S and all parts less than or equal to L plus S, and L plus S minus 1 does not appear as a part. We say that L plus S minus 1 is impermissible. And CLS2 denotes the set of partitions with all parts lying between S plus 1 and L plus S. With this notation, they conjectured that there exists a bound M which only depends on S, such that whenever N is larger than the bound, the number of partitions of N in CLS1 is more than the number of partitions of N in CLS2. For the second conjecture, they replaced the impermissible part with L instead of L plus S minus 1. So now it is independent of S, and then they made the exact same assertions. So then they tried to generalize these inequalities for an arbitrary impermissible part K instead of choosing K to be L or L plus S minus 1. However, this time they basically worked using Q-series analogs of these results. So they defined the Q-series HLS K of Q as follows. So where roughly speaking, L corresponds to the difference between the largest and smallest parts of the partition, and S corresponds to the smallest part, and K corresponds to the impermissible part of the partition. So then they conjectured that this Q series is eventually positive, meaning that all its coefficients are positive after a certain bound. Finally, for the fourth conjecture, they once again turned their attention to partitions having a difference between their largest and the smallest parts, bounded above by L. So among these partitions, they compared the number of partitions with smallest part 2 with those having smallest part 3 or more. So then they conjectured that this series has non-negative coefficients, apart from a few exceptional terms in the beginning. So we proved all of these 4 conjectures, and in fact, we proved stronger results. So we should also mention that Zhang and Zheng also gave proofs of the first 3 conjectures out of these 4. And however, our proofs and their proofs are completely different. In particular, their proofs are analytic for some cases and combinatorial for some others, whereas our methods are almost entirely combinatorial. So we use a series argument at one place, but that can be easily replaced with a combinatorial argument. So like being analytic, their methods are somewhat more straightforward than ours. However, they produce results that are asymptotic and do not give explicit bounds. Being combinatorial, our methods produce explicit bounds on when this series has positive coefficients and also lead to a proof of the fourth conjecture. So by explicit bounds, we basically mean that, so they prove that that the coefficient of q to the power n in this series is positive as n goes to infinity. And so they get that there exists a bound after which the coefficients are positive. Whereas using combinatorial methods, we get a specific number depending only on s, after which the coefficients are all positive. So next we describe a sketch of our proof of the first conjecture in the case L greater than or equal to s plus 3. When L is smaller than s plus 3, the proof is much more complex and intricate, and we won't go into the details today. So in this case, we define the quantities f of s and kappa of s, depending on f of s. So then we assert that this quantity kappa of s serves as the bound for our first conjecture in this case, meaning that whenever n is greater than or equal to kappa of s, the number of partitions of n in CLS1 is more than the number of partitions of n in CLS2. So for this, we construct an injective map between these sets. So basically, we have a partition of n in CLS2, and we want to map it to a partition of n in CLS1. Recall that CLS2 consists of partitions with all paths lying between s plus 1 and L plus s. So we can express the partition pi in the following form, where f of s plus 1 denotes the number of parts of s plus 1 in pi, which is also known as the frequency of s plus 1. So, and also recall that CLS1 denotes the set of partitions with smallest part s, all parts less than or equal to L plus s, and the impermissible part is L plus s minus 1. So to map this partition pi to a partition in L plus s minus 1, we need to basically make 3 adjustments. So first of all, we need to remove all parts of L plus s minus 1, because here L plus s minus 1 should not appear. And then we must add some parts of s, because the smallest part should be s. And finally, we should ensure that the resultant partition remains a partition of n. So basically, the norm of the final partition should be same as that of the original partition. So to define our map, we consider several different cases depending on the frequency of L plus s minus 1 in pi. So for brevity, we denote this sequence by f. Sorry, we denote this frequency by f. So our strategy for ensuring that the map phi is injective is to construct it in such a way that in different cases, the partitions in the image have different frequencies of s. So like as shown in the table, so in all the different cases, the frequencies of s come from disjoint sets. So for example, suppose we have a frequency pi1 in case 2a and a frequency pi and a partition pi2 in case 2b2. So then their images will be different, because for the image of pi1, the frequency will be a multiple of 12, whereas for the frequency of s in the image of pi2 will be 20. So they are going to be different, and we get that the map phi is injective as long as it is injective within each case. So finally, we describe our map in the various cases. Case 1, suppose that f is greater than or equal to 1. So in this case, we remove all the f parts of L plus s minus 1. And to compensate, we add back 2f minus 1 parts of s. So however, we further need to add the difference. So this difference, which can be rewritten as follows. So recall that we were in the case L greater than or equal to s plus 2. So the quantity in the bracket is greater than or equal to 1. Also, f is greater than or equal to 1. So we get that this difference is a number greater than or equal to s plus 1. And by an application of the division algorithm, we can express this number as a combination of s plus 1, s plus 2, till 2s plus 1. Basically, we are saying that this forms a reduced residue system, mod s plus 1. So we can basically add the difference by adding appropriate parts of these numbers. So thus we get the map phi in this case, and note that the frequency of S is 2f minus 1, and from there f can be recovered, and thus the map is injective within case 1. Next, we suppose for case 2, we suppose f is 0. So this time we don't have to remove any parts of L plus S minus 1, and we just need to add some parts of S and compensate by removing some other parts from the partition. So we'll have two further subcases, and for the first subcase, we assume that there exists some m in f of S which has frequency greater than or equal to 12s, and we let m naught be the least such number. So we basically remove these 12s parts of m naught and compensate by adding 12 m naught parts of S. So the image of pi has frequency of S equal to 12 m naught, and from there we can recover m naught. So the map is going to be injective in this subcase as well. And for case 2b, we have the opposite assumption. So we assume that for every m less than f of S, frequency is less than 12s. So basically for all of these numbers, the frequency is less than 12s. And since we are assuming the norm of the partition n to be large enough, greater than or equal to cap of S, such that cap of S is also chosen large enough such that we can ensure that whenever all of these frequencies are less than 12s, then there will be some parts beyond these numbers which appear with non-zero frequency. To be precise, we mean that there exists an h greater than or equal to f of S, which appears with a positive frequency, and we let L be the least such number. So a natural attempt for the image then will be to remove a part of L and compensate by adding some parts here, especially adding some parts of S. So since L is greater than or equal to f of S, we get by definition of f of S, L minus 8s is greater than or equal to this quantity, which is actually the Frobenius number of 10s minus 1 and 15s minus 2. So also these numbers can be shown to be co-prime, and thus we can express L minus 8s as a combination of 10s minus 1 and 15s minus 2. So now a natural attempt will be to remove a part of L and compensate by adding 8 parts of S and XL parts of 10s minus 1 and YL parts of 15s minus 2. However, the problem with this map will be that it will not be injective because the frequency of S in the image is 8, so that's a constant, and we cannot recover L from here. However, suppose we were given that f of 10s minus 1 was 0 and f of 15s minus 2 was also 0. So in that case, the image would have looked something like this. And then from the frequency of 10s minus 1 in the image, we could have recovered XL. Similarly, we could have recovered YL. And then from this defining equation, we could have recovered L, and the map would have been injected. So now the question is, how can we ensure that both of these frequencies are simultaneously 0? So for this, we play a trick. So whenever 5s plus 1 and 10s minus 1 appear with non-zero frequencies, we remove a part of each of them and compensate by adding 15 parts of S. So we can assume that at least one of these is 0. Similarly, if 5s plus 2 and 15s minus 2 both appear with a non-zero frequency, we can remove a part of each of them and compensate by adding 20 parts of S. So at least one of these is 0, one of these is 0. So at least 2 out of these 4 are 0. These could be these ones, or the cross ones. So accordingly, we get that at least one of these 4 statements is true. So we handle each of them similarly. And suppose T4 is true, so we get this assumption that these two frequencies are 0. And that is precisely the scenario that we want it to be in. So now the image looks like this, and we can recover XL and YL from here, and thus L, and the map will be injective. So this completes our proof of the first conjecture in this case. And so this work has recently been accepted by a journal, and we hope it will be submitted, published soon. So thanks a lot for your kind attention.
Thank you, Damanvir. It's a great talk. I want to open it to questions if anyone has any questions. So I have a question regarding those conjectures. Where did they come from originally? Was it kind of slightly put out there, or like was it related to some other work and they were just thinking about it?
Yes, so like they basically defined some maps and realized for the cases S equals 1 and S equals 2, they were not very hard to prove, and it seemed to them that they should be true in general.
Yeah, so I guess a related question. I'm curious if you solving these conjectures is like a tool that they were planning to use in something else.
So like the ultimate goal, I think, would have been to study the series GL1, GL2, and GLS in general, where we compare the number of partitions with parts having smallest part S with those having smallest part S plus 1 or more. So they proved that the number of partitions with smallest part 1 are more than the number of partitions with smallest part 2 or more. And then they conjectured the same thing for 2 and 3 or more. And so in general, it is nice to study that for any S.
If there are no other questions, let's thank Damanvir again.
Thanks a lot.